Why does your compass always point north? And what is a magnetic field? And why does Earth's magnetic north pole turn out to be a magnetic south pole? This is a conceptual introduction to magnetism. And first, let me tell you something. Every magnet has two poles, north and south. But the thing is, these poles are not like electric charge. You can have a negative charge and a positive charge, but you cannot have just a north pole or just a south pole. It's never been found a magnet with just one pole. If you cut it in half, all you get is two smaller magnets with their own poles. So poles interact similarly to charges. If you have a north and a north, they repel. Same for south and south. If you have north and south, however, since they're unlike, they will attract. Again, this feels like charges, but it's not the same. Magnetic poles always come in pairs. And because you cannot separate these poles, magnetic field lines always form closed loops. They have nowhere else to go. If you remember field lines from back in electrostatics, these are the invisible lines that we use to visualize where magnetic force exists. So I'll show you. Here's a standard magnet, and we'll have north on the left and south on the right. The field lines outside the magnet will exit from north and enter through south. What does that mean? Take a look. Out from north and into south. So the direction comes from north, right, like that. Kind of like how in an electric dipole, they come out of the positive charge and then they come into this south one. But when it's inside, they go from south to north instead of north to south. So out the loop, you go out from north into south and then back when you're inside the magnet from south to north. It's a closed loop, always. Magnetic fields never start or end, unlike electric fields, which go from positive to negative. It's a loop. Let me teach you about Earth's magnetic field, which is a bit of fun. This can be confusing. A compass needle has a north pole, which is the red end, and a south pole. The red end is attracted to north. So if the compass's north pole points toward Canada, then Canada must have a magnetic south pole because opposites attract. It attracts the north end of your compass. And Earth's magnetic field will look something like this. Similar to the kind of magnet we were looking at, but if this is the rotation of axis, so this is how it spins. Magnet is something like this with south and north. The geographic north pole would be here and south pole here. And the field lines look just like the ones that we're just looking at. They go out in this direction from the north side and enter back into here, but they start the loop again. I'm going to get rid of these field lines because we're trying to look at Earth here. Earth's north magnetic pole, the one that a compass would point toward. So the north needle, it points toward the south magnetic pole direction. So this is why the north pole is up here. And so location name is not based on magnetic polarity. And if you align your compass needle north, there is a magnetic true north. And depending on your location, the compass will deviate from this true north. This deviation is called declination. And it might be like 70 degrees in one country, but in another country it might be 5 degrees. This means magnetic north is this many degrees away from true north. And you have to consider this when you're doing navigating in aviation or military use. Let me show you uniform magnetic field. So if you remember back in electric fields, we had uniform electric fields as straight lines. Magnetic uniform fields look similar. We've got straight lines going from a north to a south. And at the ends, they also have the fringing that happens in electric field lines. When magnets have wide flat poles, the field in the middle is nearly uniform. That means all of the field lines are parallel and evenly spaced, and it mimics the behavior of a uniform electric field between two capacitor plates. But at the edges, it also fringes outward and becomes non-uniform, just like electric fields. So we now know magnetic fields always form closed loops, and they go from north to south. On the outside, Earth's field behaves the same way. Now the question is, where do these magnetic fields come from? In 1820, this guy named Hans Christian Andersen, which I'm not sure how to pronounce, but in 1820, he found something huge. A current carrying wire, so a wire that's carrying current, makes a nearby compass deflect. This proves that moving electric charges, so currents, actually generate magnetic fields. This was the first real link between electricity and magnetism. And this is what he saw. So imagine this is a wire. It's a circular loop of wire. And it's carrying a current of I. He saw that nearby compass needles deflect and they line up in a circle. So what the field lines would look like is this. What's happening here is that he realized the magnetic field isn't pointing toward or away, it's circling around the wire. We'll expand on this soon, but if you have this wire in a loop, each segment still makes circular field lines, but the field lines in the center, they add up, which means it's stronger and directional through the middle. This magnetic field in the center of the loop is like a biomagnet straight through. This is how electromagnets are built. And let me teach you a trick that's popular with people learning physics. It's called the right hand rule. It helps you find the direction of the magnetic field that a current is creating. So imagine you have a wire and you have a current of I flowing through, and you want to find the direction of the magnetic field B that surrounds it. Here are the steps. Hold out your right hand. Point your thumb in the direction of the current, and current means the flow of positive charge. And then curl your fingers around the wire. Here's the result. Your curled fingers will show the direction of the magnetic field B that loops around the wire. Why this works is it's your right hand. If the current goes up, let's say toward the ceiling, then your thumb is going to point up. And then your fingers are going to curl counterclockwise. So that means B is circling around the wire counterclockwise. How about a current that's coming out of the screen? Try and imagine this. This is the current that's coming toward you. Your thumb points at you, and your fingers curl counterclockwise. And your fingers around it will curl counterclockwise. How about for force on moving charges or currents? Use this when you're asking what direction is the force on a wire or moving charge in a magnetic field. You point your fingers in the direction of the velocity or the current I. Let's say the current's going this way. Okay, your fingers are like that. Rotate your hand so your palm faces the magnetic field, which is B, or just bend your fingers toward B. And your thumb, wherever your thumb is, now points in the direction of the force F. Let me show you. Let's say we had some magnet like this. Magnetic field is like this, and the current is coming this way. How do we align our right hand to find where the force is going? Point your fingers in the direction of the current. Okay? And then rotate your hand so your palm faces the magnetic field. Or the other thing you do is bend your fingers toward the field. So, like this, trying to draw here. And then your thumb, wherever it is now pointing in the direction of the force. So now you know the force is here. Fingers represent current and velocity. The palm and the direction that you bend it in is for the field. And then your thumb tells you where the force goes. This rule works for positive charges. If it's a negative charge, then flip the direction of your force. So if your thumb's going up here, then the force is here.